welcome to our second section of the year, Polynomial Functions of Higher Degree, section 2.2 in your notes. What we're working on here is essentially rational functions and rational expressions. And when you hear the word rational in math, or rational expressions, rational functions, it just means you're essentially going to have x raised to some whole number exponent. So the mathematical way to write out a rational expression is this right here, and of course if you wanted to make it a rational equation, you just set it equal to 0. So right now that in the notes is written as an expression, and notice that n is always a positive whole number. So we call this form standard form, because standard form always goes, if you notice right here you have n, say n was 5, that would make this whole value right here 4, the next one 3, 2, all the way down to eventually x to the first and x to the 0, which is your constant term right here. Okay. All right, when we graph these, again, this section is going to cover a lot of graphing of these rational equations. When you draw these graphs, they're going to be, the mathematical word is continuous, and what continuous means is you're going to draw it and you're never going to have to lift your pencil off the paper. What that means is, again, no lifting your pencil, but also you're never going to make a sharp turn. Like the absolute value of x, you may recall the graph, what it looks like is a v. That graph is not continuous strictly because you make a sharp turn right at the origin. Also, you may have seen other graphs in other classes, right? Sometimes you have, an ending point and then it starts up again here, and the graph, again, you're not going to see anything like that in today's section. What you are going to see is graphs that move a continuous curve from left to right. So the graphs you will see, essentially, you will have points, and I'm going to show you how to find things called zeros and points on curves. And what you would be doing is you would be connecting them in a smooth curve from left to right. What that means is this red line is an example of what could be a rational expression or a rational equation. What you are not going to see is you're never going to see something double back. So you never see a graph start to the right, hit a point, and then turn around and go back in the other direction. You will never ever see anything like that in this section, so don't draw it on any graphs, on any homeworks, any quizzes, any tests. All right. So rational functions have degrees. Degree is just a fancy word for the highest exponent value in any of the problems you're working on. You've seen x to the first, like think y equals mx plus b. I'm sure you're familiar with that. This has x to the first, it would have degree 1, right? It always graphs a line here. Graphs of degree 2, always a parabola. I'm sure you've seen y equals x squared. You know that the graph is always kind of a U shape or more like an N, depending on how it starts. Graphs of degree 3, cubics. Cubics, again, always have a very similar form. And then as we go on, a pattern starts to develop. X to the fourth looks very similar to a parabola. X to the fifth looks very similar to a cubic. And what I'm saying is x to the fourth similar, although the rate at which it rises and falls is different. But the pattern that I hope you have picked up in previous classes is right here, these two parts. If the graph has an even degree, it's going to be similar to a parabola, meaning it's going to extend either up and to the left and right to the left forever, or it's going to extend down and to the left and down and to the right forever. A cubic is exactly the opposite, or anything raised to an odd degree. It's going to be going essentially something that's cubic. It's going to always look like this, or it's always going to have, and what I'm really getting at here is end behavior. What does it do out here, out here, out here, and out here? The middle is going to be different in every graph. So that would be for odd degrees. All right, we've been going over transformations kind of as our intro. So we should be able to, given the fact that this is an x to the fifth, we should be able to say, all right, that's going to be like a cubic, and we should be able to figure out what this transformation does. We know it's kind of like a cubic shape. This negative sign is essentially going to flip it over the x-axis. So you would have it again. I'm not super particular. I'm looking for a general shape. It looks something like a cubic. It's actually not a great graph. Let's try that again. Something like a cubic that's been reflected over the x-axis. We'll do a few of these. We're going to do x to the fourth plus 1. I would hope you can recognize that that is going to be similar to a parabola. The plus 1 is a shift of up 1. So normally a parabola would pass through 0, 0. This parabola is going to pass through 0, 1. And again, it's not a parabola, but the behavior is going to look similar to the sketch of that graph is going to look similar to a parabola. I have one more down here. See if we can fit this on the graph as well. All right. Now notice that the difference here is essentially the order of operations. Here I'm asking you to add 1 to x, then raise it to the fourth. This is a completely different shift, a completely different transformation. Right here, adding 1 to x before you raise it to a power is going to move it to the left 1. Right. So again, instead of having that, it's still going to be the shape of a parabola. Instead of passing through 0, 0, it looks like it should pass through right here, and it's going to follow the shape of a parabola. So here in this slide, I want to show you guys, I'm sure you know how to use the graphing calculator, but what we're going to do is we're going to take a couple quick looks on the graphing calculator, like if f of x is equal to negative x to the third plus 4x, how do we graph that on the graphing calculator? So hopefully you have something similar to mine. We're going to want to hit the y equals button, get a screen like this. You're going to want to type in the opposite of x to the third, and the way you're going to do that is you're going to use the negative sign, not the minus sign. Negative x to the third, and then you're going to say plus 4x, plus 4. X is this button here. It's got an x, t, a 0, and an n on it. It's your variable key. And then you're going to want to graph it. And what usually a good graph is a zoom standard will get you a standard 10 by 10 window. It's the one used most often. I'm going to drag and drop this into our file here. So essentially, that is our graph of x to the third. The opposite of x to the third plus 4x. That's our graph. And what I'm really concerned with is I want to start looking at the end behaviors of these graphs. Like, so when the degree is 3, we have an end behavior going up and to the left and down and to the right. But in a polynomial of degree 4, we have an end behavior going up and to the left and up and to the right. And there's some patterns here, and I have, in the interest of time, I graphed these already. Like here's x to the fifth. We have end behavior going down and to the left and up and to the right. And hopefully you've seen some patterns here before. I'm hoping that you have graphed some polynomial expressions and that you have seen some patterns, because on the next slide, here, in a rational expression, all right, if you were to say graph this, all right, if you were to make it in an equation and graph it, then what I'm talking about, if the degree is odd, so here I'm saying if n, this number, the degree is odd and this number right here is bigger than 0, exactly what it reads, well then there's some guaranteed behavior that's going to happen. All right, this graph is going to be, I mean, obviously you can't tell what's going to happen in the middle. It's going to end going down and to the left. Who knows what's going to happen in the middle? It could rise a bunch of times, but it's got to end going up and to the right. Now, if I change that, and let me see, if I was to keep n an odd degree, meaning still, thinking kind of like a cubic. Remember we earlier said that if n is odd, it's going to behave similar to a cubic. Then what if I made the leading coefficient, again that leading coefficient is now this number here, an, if I made that negative, meaning smaller than 0, how's my graph going to be different? Well, it's going to go up and to the left forever. And again, who knows what's going to happen in the middle? But at the end behavior, it's got an end going down and to the right. Again, there's no exact way. It's very sketch-oriented right now. Not looking for exact preciseness. Right now, these are just sketches. So obviously this works for if n is an odd degree. Well, how does it change if n is an even degree? Now, if you're thinking even degrees, I hope you're thinking should look something like a parabola. If n is even and the leading coefficient is positive, all right, what's that going to look like? Well, it's going to look very similar to a parabola, meaning that's going to have the end behavior of a parabola. Who knows what's going to happen in the middle? It could, as it decreases, it could do any number of things, and eventually it's going to have, again, that end behavior similar to a parabola. Keeping n even, thinking similar to a parabola, but if the leading coefficient is negative, well, now it looks like the opposite of x squared, if you're familiar with that. So it's going to look, again, who knows what it's going to do in the middle. But the end behavior is written in solid lines, and that's what I'm expecting you to see. And that's just a good way, while there's no real way to quiz and test on this, this is a real way to say, it's one way to check your answers. If you have a rational function of fifth degree, and if you know the leading coefficient is positive, well, you should know if your graph is on the right track. So here in this slide, you're going to hear the term zeros, and we're going to hope to interpret it a couple different ways and relate it to things that you already know. Zeros of a polynomial function. What we're saying in this first point right here is if a function is of, say, degree 5, then it can have at most 5 zeros. So if you've got a question that, it's just got x to the third as its degree, and you should be looking for at most 3 zeros, so never find more. Not possible. That's just like a little way to, again, help check our answers. What that also means is if a function has, again, a degree of n, well, if n, going back to, let's say, n, if the degree was 5, well, then there's only going to be 4 changes of direction, or 4 maximums or minimums total. That's maximums and minimums combined. All right? And that's up to. So again, you should never be changing direction in terms of going up or down. If the degree was 5, it'll never change direction more than once. The easiest example of this is parabolas. Every parabola that you've ever drawn, is x squared, and there can be all sorts of numbers. Think quadratic formula. Every time you graph the parabola, it was still only one change in direction. Right? That one change, that one local minimum. Where that local minimum or where that local maximum was, different in every parabola. But again, if the degree is 2, like a quadratic, there's at most one local min or local max. All right, so going back to zeros, the terms that you could have heard this related to before. All right, well, the zero is the term that you're going to hear quite a bit in this classroom. I might say x equals, 5 is a zero of a function. Okay. Another word for zero is x equals 5 is a solution to the function. So if you found solutions, finding zeros, not too different. The difference is a zero is it's expected that you set your function equal to 0. So, it's a little tricky. For example, if I said f of x is equal to x squared plus, let's do minus, x squared minus 25, the two zeros here are going to be 5 and negative 5, because if you think of setting this equal to 0, right, add 25 both sides, you get x squared equals 25, you square root, and then when you square root, you always have to remember plus or minus in your answer. So again, the two zeros would be the two zeros, the two solutions. Another way to do this exact same problem would have been to use factoring. And if I went back here and instead of doing that work, I could have factored to get my solutions. This is a difference of squares.